Dear students, it's time and we'll start our lecture. So it will be recorded and we'll put it to the Didactica portal. So now let's continue our lectures, and now we'll begin a new topic, approximation of functions and data. So let's begin with the example. We have this given function f of x here, 2.7, and e to power this function, so x plus 2 over 3 squared. So we need to find here, for example, derivative or integral. So, but how to find it? This is not easy to find by hand. So we will use here our program to find this for this kind of functions, derivative or integral. But when we find by MATLAB or Octave, we need to work here not for this function. We need to approximate this function to another function which is close to this function. So in this case, we will substitute this exact function with another one, and which is either to derivative or integrate, and which is similar to it on a certain intervals of interest. For example, here a polynomial p of x. So we will consider this kind of polynomial, and we will approximate our function f of x to the polynomial. And it's called polynomial approximation of function. So here you can see in blue the function of the graph of the function f of x on this graph, and on the yellow it is the function graph of the function p of x, graph of this polynomial p of x. And here in the circle we denoted evaluations of the exact functions. In this case, how much? 1, 2, 3, 4, 5 evaluation points here. However, we need to find these coefficients, A5, A4, 3, 2, 1, and 0, yeah, here. 6, we have 6 evaluation points, not 5, 6 evaluation points. So we will define these coefficients after evaluation. Okay, now so we have set of points. Let's consider it in generally. We have set of points x, I, y, I, where I changes from 1 till m. And we want first case, let an m-1 degree polynomial pass for those m points. Here you have n-1 degree polynomial, graph of this n-1 degree polynomial, and you need to find these m points here, evaluation points. This is called polynomial interpolation. And second case, let allow degree polynomial first, second, and third. You have exact degree here, not m-1, just low degree. And through each of those m points. This is called now piecewise polynomial interpolation. You can see this is in yellow here. In brown, you have polynomial interpolation. In yellow, you have piecewise polynomial interpolation. In mathematical terms, it means choosing a class Fn, where Fn of x, the family of these functions, and a particular function Fnx. In this class following the criterion, given the points, set of points xy, yy, yi, I, where I changes from 1 till m, and find the particular Fn of x from Fn. that passes through all the points, or it satisfies this equation fn of xi equals to yi. So to each point xi correspond yi with the rule fn. I here from 1 till m. So this is m here, the maximum number of the points. And now, problem data are an interval AB and the set of n plus 1 points xi, yi inside the interval with the equation yi equals to f of xi for some function f that we want to approximate. Let's consider the xi as distinct points. We will call it nodes. So it means xi is not equal to xg for all I not equal to g. So now, here we have the definition of polynomial interpolation. Fn equals to Pn. This is a set of polynomials. It's equals to Pn of x, this polynomial, where Pn, polynomial of degree n. And the generic degree n polynomial is written as like this, you know, from course mathematical analysis and the first part of linear algebra and geometry. So here it's written the nth degree polynomial with the coefficients ai, where I changes from 0 till n. This is nth degree polynomial. We want then to determine the n plus 1 coefficients ai of the polynomial by imposing the interpolation property. So it means the passing through the n plus 1 points. So here we have how many coefficients? A0, A1, A2, etc., An. Here we have n plus 1 coefficients, yeah? So we need to find these nodes and these evaluation points where ai, we denote ai and I change from 0 till n. Here we have how many? N plus 1 points. And it satisfies this equation, Pn of xi equals to yi. So we have here what? We have here system of equations. How many equations we get? N plus 1 equations, of course. Because we will begin from 0 till n. It will be n plus 1 equation here. So, and now, here we get this system. Now, this is linear system. We said this is linear system of n plus 1 equations and n plus 1 unknowns. You can see here. And we'll build what? These matrices consisting of this here nodes we have 1 x0 till x0 nth power, etc. Here we have matrix of the unknown coefficients from a0 till an, and here we have yi. So like ax is b. We will solve this equation now, the matrix equation. And this system matrix is called Vandermonde matrix. This system, again, we call Vandermonde matrix. And it is non-singular if the xi nodes are distinct. Hence, the polynomial is unique here. So our Pn given polynomial will be unique. And strongly ill-conditioned when n is large. So here we have not a good way to find these polynomial coefficients. If n is large, so it will be strongly ill-conditioned system. In MATLAB, you can see how to solve this example. So we have exact function. Then we have the number of coefficients, for example, here 5. And we have xi, so nodes will give it with line space. So what does it mean, this line space? So this line space means it's generated linear vectors here. So from -5 till 5, n plus 1 vectors it will generate with this command, line space. If we wrote just -5 and 5, it generated automatically 100 vectors here, linear vectors. But in this case, we can give value of this vectors, so number of this vector here, n plus 1, because of we have n plus 1 nodes. And the yi here, we will put to the exact function the value of xi. Yes, from our given example. This case, let me one more time show you. This fn xi equals to yi, I from 1 till m. So is it clear? Can you hear me, guys?
Yes.
Okay. Now, the next step, we will interpolate this function. So finding a with the common polyfit. So it's equals to x. So it is from xi, yi, and n. We will find these coefficients of the interpolating polynomial here from a0 till an. And now here again, interpolate now evaluation. In this case, p, this is command polyval. It means polynomial evaluation at values in x here from a till x, and then plot the graph. So with the command plot, we will do such kind of examples in practice lessons also. So x, it is x, and then f exact value, f exact function, and here we will put minus. It means this is denoted with minus it. So you can see here just straight line this is. So in blue, you can see in blue, and here the next one, xi, yi, this is just with circle. This is circle. With circles, it gives us evaluation points, 1, 2, 3, 4, 5, 6 evaluation points, and polynomial evaluation function yp. So this is with double straight line as double this diffuse. So it means here we have this kind of in yellow. You can see this is in yellow, interpolating polynomial it is. This one is interpolating nodes. This is exact function. We have in one plot 3 graphs. Graph of exact function, graph of interpolating nodes, and graph of interpolating polynomial. Okay, let's continue. And now the solution of the wonder mode system is not a good choice. If ill conditioning and large n, we need to find the alternative representation of this interpolating polynomial. It's not good for us if it's in ill conditioned and with large n. So now let's consider again our polynomial Pn of x, and here correspond to choosing from 1 till xn polynomials as base of the class of polynomials Pn with degree n. And let's try to choose a different base, the n plus 1 LG polynomials of degree n. So LG polynomials take value from 1. So if 1 on the xg node and 0 on all other xi nodes. So it takes 2 values, you can see here. 1 on xg node and 0 on otherwise xi nodes. So here we will build this LG polynomial with the product of these factors. So here we can see it's product of x minus xi over all products of xg minus xi. G here change from 0 till n. So this is called fundamental Lagrange polynomials associated to the x0, xn nodes. Again, this is fundamental Lagrange polynomials. So here you can see the graph of LG of x. In blue, it is L0 of x. In blue, L0 of x. L1 here is this brown one. And then yellow one is L2 of x. It changes, you can see. And L3 is violet. So here written in 4 points, 0, 1, 2, and 3. 0, 1, 2, 3, this is G. This is G. Okay, now. So given that this Lagrange, fundamental Lagrange polynomial, and we said it takes value 1 on xg and 0 on the other xi. So, and we can write here this polynomial Pn of x as in this form. So Pn of x, this is sum of yj lj and y0 l, it's equals to y0 l0 plus y1 l1, etc. plus yn and ln. So we wrote this, our polynomial given Pn of x, this one, Pn of x in this form with the sum and using our L function, using our LJ function. So now, this is called Lagrange representation of the interpolating polynomial. This is Lagrange representation of interpolating polynomial. So here, this is yj, this is values of function which we want to approximate. And we can call it problem data. We need to find this yj. So We need to approximate it. And now let's verify that Pn xi, look here, instead of x, we will put xi. And it's equals to sum of yj lj of xi, where it's equals to, here we have i's term also. From 0 till n, we have i's term. And it will be just yi li of xi. And this is equals to yi. So this interpolation is satisfied. I here from 0 till n. So this is alternative representation of our polynomial, our previous polynomial, Pn of x. So one more time, approximation, this is replacing your function or your polynomial to another function which is useful to work, useful to compute. And this function should be closer to your function. Is it clear? So it should be closer. It's not should be same functions, should be closer function. Then it will be approximation of the previous given function. Here we consider it Wonder mode system, but it's not also a good way to compute when it's ill-conditioned problem. So that's why we find here new representation, and this representation we call Lagrange representation, this kind of representation. And we will work with this representation. Okay, now exercise. Given 3 points, xi, yi, I here from 0 till 2, of course, because of 3 points. And they are equidistant abscisses on -1 and 1 interval. Equidistant, you know, I think. Equal distant, yeah. Write the expression of the Lagrange fundamental polynomials associated with the given nodes. So 3 equidistant abscisses on -1 and 1 interval, they are -1, 0, and 1. Yes? Is it clear? Why -1, 0, and 1? Students?
It's clear.
Yeah, it's not so hard to understand. And here we have what we have, this L function from this definition. From this definition, yeah, just we put instead of xi and xj this our nodes here. So it will be x minus x1, x minus x2, then x0 minus x1, x0 minus x2. You can see here as g we consider here in L0 x0. As other ones will be xi. Look here, xi, and you have xj. So j here is 0. In the second case, j is 1. Third case, j is 2. And now we get here x minus 0, x minus 1 after replacing substitution, yeah, and -1 minus 0, -1 minus 1 here. So you get 1/2. We obtain 1/2 x minus 1. This is for x0 when j is 0. And let's consider j is 1. And when j is 1, we obtain this kind of factors, minus x plus 1 and x minus 1. So this is when j is 1. And the next case, j is 2. So here it will be x2. Denominator, x2, x2. We just replace our j here. You can see here j, because of lj. L depends on j. So here x minus xi, and here j. And when j is 2, it will be 1 over 2 x plus 1 times x. So we have 3 values here, 3 functions, new functions now. And now they are this Lagrange fundamental polynomials, because of here written this LJX fundamental Lagrange polynomials associated to x0 and xn nodes. In our case, they are Lagrange fundamental polynomials associated with these given nodes 0, 1, and x0, x1, and x2, with these 3 nodes. And now, let's consider the next example. Given the interval and the nodes of the previous exercise, build the Lagrange interpolation polynomial of degree 2 for the function f of x 9 plus x squared, the power of -1 function. So here, let's consider, so nodes same, -1, 0, and 1 with the previous example, 3 equidistant abscisses on the interval -1 and 1. Now, we have the function yi equals to fxi. So let's put here, instead of xi, to here. Look here, f of x, because f of x 9 plus x squared. Let's put, for example, -1. It will be 9 plus 1 to power -1. So this is 1 over 10. And when we put 0, it will be just 9 and 1 over 9. If you put 1, it will be again 1 over 9. So we have these corresponding values of yi, 1 over 10, 1 over 9, and 1 over 10. And we have the expression of the Lagrange fundamental polynomials, L0, L1, and L2 from the previous exercise. And the interpolating polynomial here will be, look here. However, here P2 of x, because we have Pi, I changed from 1 till 2, from 0 till 2, sorry. And now it will be the sum of all these L0, L1, and L2. This is Lagrange interpolation polynomial. You can see from the definition, of course, here, Pn of x, this is sum of this Lagrange polynomials, fundamental polynomials here. And then it will be Pn, in this case, P2 of x. This is the sum of this interpolating these fundamental Lagrange polynomials. So now, and now remark, if you want to have a coefficients of expression P2, so there is coefficients A0, A1, and A2. In our case, it is 1 over 10, 1 over 9, and 1 over 10, yeah? So we have to develop all the products and divisions. This is, however, unnecessary at the aims of the practical use of this polynomial. Now, I think that with this example, you can understand this example. Now, let's continue. Do you have any questions here? Students?
While not.
You don't have any questions here, yeah. Okay. Now, let's continue. So, in the previous slide, we saw how to approximate function f of x by the interpolating. So here we approximated our function f of x with this polynomial. The aim was approximated to the polynomial, to the Lagrange interpolation polynomial. So now we have nodes x0 and in this case x0, x1, and x2. Now, when we approximate our function to the polynomials of degree n with nodes x0, xn, we have some kind of errors because of this is not exact function. Yeah, this is approximation of function. It's close to our exact function. And how to find now this error? So error here is just e, we denote e and x here, and this is f of x minus this p n of x. We call interpolation error. F of x is exact function. P n of x, this is polynomial of polynomial p n of degree n. And remark, the first case, the first equation where e n x I equals to 0, we call it interpolation criterion. It's called interpolation criterion, where e n x I where equals to f of xi minus p n of xi in exact value of xi where equals to 0, it's interpolation criterion. And the second one, e n x is 0 for all x from a b interval and for all f from set of class of polynomial m's degree. This is interpolating polynomial unicity. So we can find here error when we do interpolation, when we do approximation. So again, this is interpolating error. And let's define uniform norm of a continuous function g of x over interval a, b. So this norm, uniform norm, it's equals to maximum value of g of x, absolute value, of course, here. This is norm of g. If f of x is continuous in closed interval a, b, and the nodes xi are also in a, b, and here the measure of error en equals to the norm of f minus pn. F minus pn. Uniform norm of f minus pn. So we will say that sequence pn, sequence of polynomials, is uniformly converged to f if and only if the limit is equals to 0. It's known you from course mathematical analysis. So here, when they will be convergent, so when this limit equals to 0 as n tends to infinity. Okay, now, so here we find this error, measure of this error, and when it will be uniformly convergent. This p n sequence to function, exact function f. Okay. Which sequence we are interested in? Let's start by fixing an infinite sequence of distinct nodes on the interval a, b. For x0, 0, we correspond the polynomial p0. If x0, x1, it will be P1. If x1, x0, x1, and x2, it will be P2. If it is x0 till xn, it will be Pn of x, yeah? We correspond to the polynomials, Pn. And now you can see we built what? The sequence of polynomials, P0, P1, P2, etc., Pn. So this is sequence of interpolating polynomials associated to the xi and nodes. From the definition, the sequence converges if uniform converges, of course here, if this limit as n tends to infinity uniform norm of Pnx minus f of x equals to limit of, here again, from this definition, maximum value of this Pnx minus f of x, and it's equals to 0. Only in this case, this sequence converges, Pn of x converges. So one more time, here we have sequences. You can see 0 and 1, 2, etc. n. We have corresponding nodes also, xi. So after building this sequence, we will answer to the question when it will converge. And converge when it satisfies this condition. So limit equals to 0. This is from the previous slide. So here you can see limit when it's when Pn converges uniformly to f when the limit is 0, and this uniform norm we can define by this way, maximum of g of x. So we change this uniform norm to the maximum of this absolute value for continuous function, of course. Okay, now if we build this sequence of interpolation on growing numbers of nodes, will it be always converging to exact f of x? So your P0, P1, P2, P3, Pn of x, we have growing numbers of nodes from 0 till n, and the question, will it be always converging to the f of x? Let's consider two examples. In first case, f of x, it is 2.7 e to power x plus minus x plus 2 over 3 squared. And you can see here in blue exact function f of x. Then we have P3, P5, and P7. Graph of P3, P5, and P7. The brown, you have graph of P3, on the yellow P5, and on the violet P7. So you can see here, do we have converging here to exact function? Yes, because it's very close to our exact function, our f of x in blue. Yes? So we can say here, yes, it's converges to exact function f of x. But if we consider the second function, in this situation, f of x is equals to 1 over 1 plus x squared. You can see the graph of 1 over 1 plus x squared in blue. And you can see the graph of corresponding interpolations, P4, P8, and P12. Here, P4 in brown, P8 in yellow and the P12 in violet, yeah? So in this case, they are not same. You can see there's difference between them. They are not close to our exact function in blue. So here we will say no, because of they are not close to our exact function. Interpolating here, not convert to the exact function. So you have two examples to understand. Will it be always converged to exact f of x? So in general, the answer is no. Because so we consider this example also. So in generally, it will be no. And it can be proved that, remark here, given any sequence of distinct nodes on A and B interval, it always exists a function f of x, continuous function on the interval AB, which generates a sequence of interpolating polynomials, which doesn't uniformly converge to f of x in AB. This is general answer to our question. So, doesn't uniformly, which generates a sequence of interpolating which doesn't uniformly converge to f of x. Not in all cases, it's true. Okay, now, typical choice for a sequence of distinct nodes in A, B. First situation, equidistant nodes. How to define these equidistant nodes? With this equation. Xi is A plus B minus I, B minus A over N times I from 0 till N. So we get equidistant nodes. So we considered case where we have 3 equidistant nodes on the interval -1 and 1. -1, 0, and 1. And the second case, Chebyshev-Lobato nodes. So here it's defined with this equation, Chebyshev-Lobato nodes. It's equals to A minus B over 2 cosine I over N pi plus A plus B over 2, where I from 0 till N. And you can see here how they situated, how they represented. So they are Chebyshev-Lobato nodes. Chebyshev-Lobato nodes. On the circle, you can see. And the third one, Chebyshev nodes. So it defined with this formula. A minus B over 2 cosine 2i plus 1 pi over 2 and plus 1 and plus A plus B over 2, where I from 0 till N. And here you can see how they placed these Chebyshev nodes now on the yellow. They are Chebyshev nodes. This is Chebyshev-Lobato nodes, and they are Chebyshev nodes. So we have 3 kind of choices. We can choose these equidistant nodes, or we can choose these Chebyshev-Lobato nodes, or we can choose these Chebyshev nodes. It depends on your problem. It depends on your algorithm. Okay, is it clear? Now let's continue. So example of converges, non-converges polynomials, interpolations. So first example, same function f of z and same choice of equidistant nodes, but different intervals. Again, let's consider this function. It's called Runge function. And here on the interval -5 and 5, and on the interval 1, 2. So you can see on the interval -5 and 5, they are non-convergent. Yeah, because of, again, this is the graph of the exact function, and this interpolation polynomials are not close to our graph. From this graph, you can see this is non-convergent on the interval -5 and 5. But on the interval 1 and 2, you can see they are same. So it means it's convergence. Yes? We have same function and same choice of nodes, just equidistant nodes we have, but different intervals. And we have two different answers. On the first case, on the first situation, it is non-convergence. On the second one, it's convergence. Is it clear? So it can be different. One example can be different. It depends on your interval also.
Professor?
Yeah.
Could you tell me what's the main difference between non-convergence and convergence?
Okay. Convergence, this is limit is 0 here. We gave it. So let me, this one. Here, if this limit is 0, this is convergence. So you have your polynomial, Pn of x, and your exact function, f of x.
And
if its limit is 0, this is converged. If it's not 0, this is non-converged.
thank you, I got it.
Okay,
Yes.
so it means P and x and the f of x very close in as n tends to infinity. That's why it called converge. So, but in this case, you can see on the interval -5 and 5, it's not non-convergence. On 1, 2, it's converged. They are same graphs they have. But in this case, not same. And the second one, same function f of z, different choice of nodes. So what kind of function? Again, Runge function. We consider 1 over 1 plus x squared. Here, again, when equidistant nodes, we considered it. This is non-converged here, yes? Because you can see graph is not close to our graph of interpolation polynomials. But in Chebyshev nodes, it's close to our graph. You can see here, yes? This is converged. So, conclusion. Convergence and non-convergence depend on type of nodes, depend on intervals. So, it can be different choice of nodes and different type of convergence or non-convergence. Or it can be same nodes and same function, but different intervals. And here also we have different answers. Okay, now, If you don't have any questions here, we will continue. Is it clear, students? So, okay, let's continue. And now, for Chebyshev-Lobato and Chebyshev nodes, can we prove that the sequence, this Pn of x polynomial sequence of the interpolating polynomials uniformly converges to f for any f of class C1. What does it mean, C1? Class of continuous function, AB, on the interval AB, at the number nodes grows to infinity. If Pn of x, the sequence of interpolating polynomials associated with Chebyshev-Lobato or Chebyshev nodes in the interval AB, then we have this condition. So f from C K A B, it means K times differentiable, continuous differentiable K times on the interval AB, a function from this class, then uniform norm of f minus Pn, it's equals to small o of logarithm n over n to power k. So they will converge with this order. Here also written, in other words, continuity and differentiable of f should converge for the Chebyshev-Lobato and Chebyshev nodes, and for the regularity differentiable up to order k here implies quicker convergence here. So for Chebyshev-Lobato and Chebyshev nodes, sequence uniformly converges to f for any f of class C1. For any function of classes C1. So we can summarize here, increasing the degree n of interpolation polynomial doesn't necessarily mean we are getting a better approximation of a function f. We consider this example, yes? So it's not good idea to continue here. If n is large, this is not good for us. Second one, the uniform convergence of an interpolating polynomial to the desired function f depends on the choice of interpolation nodes and on the f regularity. Third one, choosing equidistant nodes doesn't guarantee uniform convergence, even for a differentiable function of any order. So we consider this example also. If we choose these equidistant nodes, it's not always converged here. Converged function will converged polynomial will get. And last one, if f is continuous and differentiable, the choice of Chebyshev or Chebyshev-Lobato nodes does guarantee uniform convergence. So we considered if f is differentiable, it's always converges for Chebyshev-Lobato and Chebyshev nodes. From these examples also, you can consider here a Runge function and Chebyshev nodes. Yeah, this is converges. But for equidistant nodes, it's not converged. The difference between equidistant nodes, Chebyshev-Lobato nodes, and Chebyshev nodes here written. So they define with different equations. They are Chebyshev-Lobato and Chebyshev-Floyd on the circle. We will define them. So here equidistant nodes on the green, on the red Chebyshev-Lobato nodes, and on the yellow Chebyshev nodes. So for these nodes, function, especially this if function continuous and differentiable, here also written, yeah? If it is from C1 class, so it is continuous and differentiable on the class AB. And this gives us uniformly converges to F of our Pn of X. And for class differentiable up to order K, also the function converges. I mean, Pn sequence converges to the exact function of F. That's all for this lesson. The next time we will again continue our lecture. It will be tomorrow. Do you have any questions now, students? Please give your questions.
Professor, can you advise some book which we can practice?
Yeah, of course. We have book. So let me now share this book. Let me close this demonstration. Can I close this demonstration? Yes. Okay.
Yes.
Now, I will show you what kind of books. Just a second. I said about this book on the first lecture also. So this is textbook Quarteroni, Salera in Gervasio, Scientific Computing with MATLAB and Octave. This book. You have this book on your Telegram channel, Telegram group. And we will provide lessons with this book also. Okay?
Yes. Can you share with this presentation in the Telegram group?
Okay, I will share it.
Thank you.
Any other questions, please?
No. Thank you.
And today we have also practice for groups ME1 and ME2. Okay, if you don't have any questions, we will finish our today's lecture. So now we will provide these lectures with via this Zoom meetings. Is it comfortable for you, or? I think, and we will put this recorded videos of this lecture to portal, Didactica portal also. Okay, if you don't have any questions, thank you for attention.
Thank you. Goodbye.
Thank you. Goodbye.